Okay, welcome back. Let's talk in a little more detail about the anatomy of files, how they're described, what they're useful for. I've got a pretty good selection of files that came out of a box that I had stored in my basement, and I haven't seen these guys for some time, and I can see that they're worse for having been stored downstairs. So there's going to be a little bit of cleanup and restoration that we do to these a few of these files later on, where we bust that rust off them and give them a fine coat of oil to properly preserve them. But one of the most important things that I can tell you about maintaining the files that you have is to never allow them to come in contact with each other, because the one thing that will readily dull a file is impact or contact with another file. So that's why I have these all spread out, and when they're stored and put away, they will be on something that keeps them from coming in contact with each other. So anyway, let's dial back a little bit to the beginning of the use of files. And if you can imagine that once upon a time these were made by hand, somebody would forge out the shape from what they called a blank, and then the teeth would be cut in using a hammer and chisel. But sometime around the 1860s, files started to become mass-produced. And today, mass-produced files are made of a high-grade carbon steel. So we've learned in some of the other modules about how the particular type of steel that a tool or a thing is made out of has a lot to do with the capabilities of that material. So high-grade carbon steel is a steel that has been alloyed, or steel that's been amended in some ways by having its carbon content modified, and by introducing other alloying elements like a nickel or chromium or molybdenum or vanadium to those to that steel to give us something that has the mechanical properties that we're looking for. So in a file, we're looking for something that's capable of cutting other materials, so we need it to be a material that really has the capacity for hardness, right? So it is made out of this high-grade carbon steel, and then it is heat treated in such a way that it has compressed the structure of the material to give it a high resistance to wear. So that makes it last a lot longer and cut a lot more efficiently. That's a combination of the two, a good alloy and proper heat treating or tempering of that material, gives us that tremendous capacity to cut other hard materials. Now, nothing comes without a cost, so the trade-off is that when we harden these files through heat treatment in a way that makes them highly resistant to wear, we're sacrificing most all of its ability to bend, or what we sometimes refer to as its ductile properties. So files, thin files, are highly prone to breaking. If they're bent excessively, they will shatter. And when they break, it breaks with a really sharp edge. Larger files, if they're subjected to enough stress that they shatter, they can actually launch or project small bits of that material that have this compressed stored energy in them that makes it hard, and those things can come off with enough velocity to injure an eye or to penetrate skin. So be mindful that you never want to use a file as a can opener or a lever, or or exceed its ability to flex. So files are characterized by their shape, right? So that shape could be a square or a round or a rectangle. We have what other shapes do we have here? We have some file surfaces that are convex and some file surfaces that are concave. We have files whose shapes are tapered, or files whose shapes have parallel sides, and then we have the cut of the teeth. So when those teeth are cut in by machine, if they're cut in with and only move in one direction, like we have on this mill file here, then that is called a single cut. When you have cuts going in two directions, like we have on these two files, then that is referred to as a double cut. Files that, like these two files that are used for woodworking and work on some plastics, but also work very well on leather, are referred to as a rasp tooth or a rasp cut tooth. And then over here we have that, what I showed just a second ago, we have that curved tooth where it's not in a straight line, it's an arcing tooth. Now the third and last characterization that we use to describe files is the coarseness of the teeth. So the coarseness of files is referred to as a rough tooth. Then after that comes a coarse tooth, then a bastard tooth, then a second cut tooth, a smooth tooth, and a dead smooth tooth. And we'll see some different examples of those as we go through specific files. So very briefly, let's go over file safety. We already talked about never bending them to excess or using them to pry with. It always has to be used dry, and make sure that you have proper eye protection on when you're using a file, because depending on that type of file and how coarse that file is, it may make particles that can be like, as vicious as fish hooks. And so we always want to protect our eyes, and under some circumstances it would be highly advisable to wear gloves on your hand as well. It's also important to understand that files are not intended to be used without handles on them. So the tang of a file is typically contained within a handle, and we'll look at some different handle styles later on in the discussion. So let's talk about file care. We already mentioned they have to be kept dry, and we also talked about how we never want to let a file touch another file or impact a hardened surface or come in contact with hardened hardware, right? We also want to make sure that we clean our files frequently because debris can get caught in what's called the gullet or the valleys under that tooth. And if the material gets caught up under that, it's referred to as pinning. And if you're working with wood, it can be, kind of a pain in the process because it loads up and then you have to stop and you take this file card, which has a pick and has a brush on one side, and you strike in parallel with those teeth, and that cleans that material out. But this what's called a machinist file is typically used for the rapid removal of material where the surface appearances are a secondary concern. So they come in various shapes and sizes, and they are almost always double cut. The mill file, in contrast to that, is always a single cut across the file. It tapers during the last third of the file, and it gives you a much smoother finish. And it's excellent for a technique that we're going to talk about a little bit more in a second called draw filing. And it's also excellent for using on the lathe, and it works well for filing brass and bronze. We also have what are called Swiss pattern files or jeweler's files like we have here, and needle files like we have here. So these Swiss pattern files and jeweler's files are a super smooth finish. They're primarily used by tool and die making people and people doing small scale precision work. Then we have the family of rasps, where the teeth are individually formed. They're not formed as a row. And rapid removal of soft materials is where those really excel. And when I say soft materials, I mean anything from hardwoods to some dense plastics and laminated leather as well. And then we have special purpose files that would be things like files that are just made for plastics, like we have here, type A files, which are only made for aluminum, and then what are called safe edge files. Safe edge file most files have a toothed edge on all sides. A safe edge file has a smooth edge on one or two sides so that you're able to go up into a corner and just take material off one side without affecting the other side. So it gives you a higher level of precision control. We're going to go into more detail about how to hold onto files by hand, and talk about how important it is to have the work secured so that your hands are free to concentrate on using the tool correctly, how to get a feel for what is the right amount of pressure to use when you're filing. We're going to demonstrate straight filing when we're moving with the length of our material, cross filing when we're moving perpendicular to the surface, at 45 degrees, and draw filing when we're perpendicular to the surface of that work that we're going through for an ultra-fine finish. So we're going to move in for a closer look at at the area where we're going to actually be using these, and we'll be right back in just one second. So over the course of these lecture series, we've talked a lot about how choosing the right tool for the right job is critical to good outcomes. And in tooth cutting, this is particularly true because we have to make sure that we're getting a tooth configuration that's sensitive to the type of material that we're working with and the thickness of the cross section that we're working on. Okay? So when it comes to tooth cutting, we've talked before about how if I tried to go over a thin cross section with a coarse tooth, it would jump and bounce and bend it and deform that material. So by increasing the thickness of the cross section in a way that's sensitive to the teeth, having a minimum of 3 teeth in contact with the material at any given time is the rule of thumb that we use for both saw blades and for files as well. So what I've done here is I've selected 3 files that are a good length and a good width for the material that I'm working with. And I'm starting out with a relatively coarse second cut file to try to knock this material down. And what I'm having to do here is create a taper that I've marked out with a scribed line and then blocked in with Sharpie over the top of that, because this pin has to be tapered to fit into this slot properly. So I'm going to take this material down with a series of passes with that machinist file, and again, that's a double cut file, so it's going to give us a relatively rough surface, but it will rapidly remove that material. So the advantage of working longitudinally with that length of the material is it tends to keep the material nice and flat. But because you're working over so much surface area at once, it takes a lot of force to do that. So what we'll often do for the initial stages of that filing is to come in at about 45 degrees. And what we're going to do is we're going to start on, and again, we have a handle on our file to protect our hand so that we're not trying to hold it by the tang. That gives us much better grip and leverage. We've got our alternate hand out on the end to balance it and try and make that pressure uniform, because I can't just do that with one hand because this end's going to run loose and sloppy, right? And so what I'm going to do is I'm going to start on this end and I'm going to advance forward, pushing at a diagonal like this, which is going to allow me to remove that material more rapidly. And then for my last few strokes when I come in, I'll come across the top of it to make sure that it's dead flat. So let's hit that with a few strokes. When I'm trying to take out a lot of material across a wider cross section like this, what I'll often do to make the job a little bit easier for me is that rather than coming in and just coming across the surface flat, I might come in at a slight angle and take one side down, then take the other side down, then bring that top down to meet it and flatten that out. So, there's our diagonal facet on this side. I brought that across on the other side, and now I'll come across and flatten the top out. You can see some of that pinning that I talked about occurring where a little bit of debris is getting caught up inside of the teeth. And that impedes progress, and it also scratches the surface of our material. So again, that's where the card file comes in, where we're able to take that and strike in the direction of the cuts, and it cleans that material out that is pinning under the teeth and loading up in it and slowing down our progress. Once I got the bulk of this material knocked down, I came in and chamfered or beveled the edges on all four sides because the opening that this is going into has slightly radius corners. Then after I knocked that down a little bit, I came back in with those long straight cuts using that second cut to just flatten the top of that out beautifully, right? So I knew that I was nice and perfectly straight and flat. Then I went with my single cut, and I came back in, came over the top of that, just to smooth that out and give me a nice slick surface. I'll then come back around and radius all these other edges, and then we'll do a fit up and see how it's working with the space that this is going to key into. Well, I have to say I'm pretty pleased with the way that this pin fits up in the yoke and is holding this assembly in place. As this rides up on the leg of the vise towards the head, it will tighten up. So I think we're in pretty good shape here. Again, I want it to be a hand fit that maybe just requires a little bit of a tap to grab in there, so that it's easy to install and to take it out of place. And the additional tension of the load of this vise resting down on the yoke should secure that in place. So when we get to mounting this onto the table, we'll see how it's all hanging. Because there really is no rest for the wicked, I found myself up early this morning going about getting the hardware together to mount this onto my bench. Now, mind you, blacksmith's leg vices like this are not typically mounted onto a bench. They're more commonly mounted off of a piece of angle iron and plate that's attached to a wall, or they are also commonly mounted to a large stump that has enough mass to it that it provides a balance point for that vise. And then the leg that goes down to the ground would be dropped into a hole that's countersunk into a concrete or into whatever the surface is underneath it. So what I've done instead is I went ahead and mounted it to the edge of my bench. That yoke is attached with bolts, and I've used bolts that have smooth shafts on them so that they don't mar up the maple top of this workbench that they're mounted to. So I did some measurements to calculate how high my block that I'm placing underneath it needs to be, and I went ahead and got that drilled and got that mounted in place this morning. So again, this is not really a conventional use of a blacksmith's leg vise, but because there are so many attributes to a blacksmith's leg vise, I'm adapting it in this way because it is, for me, it's not just a beautiful object, it's a exceptionally well-crafted and highly functional work-holding system. I thought while we're at it, we should just look at this little guy here that is, I know you've heard me preaching about how typically when you have something that combines multiple functions together, it usually doesn't do either of those very well on there as they would if that tool is dedicated just that task. But this is a little benchtop vise that includes a sturdy flat bed and an anvil horn on it. Unlike the blacksmith's leg vise, which is drop forged steel, this is made out of cast iron, so it can't absorb the kind of impact that other vise can. But you know, it's just cute as the workday is long, so I wanted to share that guy with you. Thanks for hanging in there with me on this project. I really would appreciate any input that you all would like to contribute to in terms of topics you'd like me to cover. So let's do this together. Thanks so much for participating.